let's look at a couple more examples of hypothesis test using means, okay? Remember, when we're using hypothesis test with means, we will be using our t-test feature in our stat test menu. And to get our critical values, we will be using this chart over the t distribution. When we're working with means, use mean Mr. T, use the t distribution. Okay. All right. Remember that there are a couple of criteria that we have to meet in order to use that feature in our calculator and the t distribution and all that. One of those criteria, the big one that we got to be aware of here, is that you either have to have a normal distribution, or the population has to be from a normal distribution, or the sample size has to be larger than 30, okay, greater than or equal to 30. So that becomes an issue for this one right here. And let me show you what's different about this one. Michael Sullivan, the author of our textbook, has decided to enroll in a reading course that allegedly increases reading speed and comprehension. Now, point out there, if you allegedly increases the speed, okay, that's a claim. So when we get ready to write our null and alternative hypothesis in a minute, that's going to be our H1. That's going to be our alternative hypothesis. That's the claim. If it allegedly increases the speed, that sounds like a claim. If you're going to take a class for reading speed, a speed reading class, and they go, oh, it's going to make you read slower, you're not going to sign up for that class. You want to hear them say, oh, it's going to make you read faster. It's going to increase your speed. It's going to make you comprehend more. That's when you're going to sign up. Okay. All right, so prior to enrolling in the class, Michael reads 198 words a minute. Okay, so that's his mean before he ever takes the class is 198. That's going to be our null hypothesis, that his mean is 198. Now, if the class is supposed to speed him up, make him read faster, that's the claim, then after the class, his mean should be greater than 198. This is going to be a right-tailed test. Okay? All right, keep that in the back of your mind. Now, the following data represent the words per minute read for 10 different passages read after the course. So in other words, he takes the class, and then instead of just reading one paragraph or something and go, well, am I faster or not? He decides, you know what, I need to do this in a statistical way. I'm going to read 10 passages, and I'm going to record how many words per minute I read for those 10 passages. And there's his results. So notice this first one, 206. Yeah, that was definitely higher than the 198. Seems like, maybe the class helped. The next one, look at that, 217. That's definitely higher. And then we get 197. And 197 is lower. Well, I wonder if, maybe that passage was really hard. Maybe it had a bunch of really big words in it, and so made him slow down, or it was a topic that was confusing for him and made him slow down. There's another 197. So, we're not sure. Not all of these 10 passages were faster. And as we talk about practical significance versus statistical significance, is 200 or 206, is that enough higher than 198 to really say, yeah, it made a big difference in his day-to-day life? We don't know yet. Okay. Now, notice they only had 10 passages. Remember, for us to be able to use a hypothesis test, we need 30. We don't have 30. Or it has to be a normal distribution. Okay. So since this is not over 30, we need to make sure it's a normal distribution. Okay, that's what it says right here. Because the sample size is small, we must verify that reading speed is normally distributed and the sample doesn't have any outliers. So the normal probability plot, that's a QQ plot, that's given to us right here, and a box plot is given. Are the conditions for testing the hypothesis satisfied? In other words, is this a normal distribution so that we can carry on? Because we didn't have more than 30. All right, well, in this QQ plot here, remember they put the raw scores on the x-axis and the z-scores on the y-axis. And we want to see if it's a perfectly straight line. We studied that back in Chapter 4. Well, it's not a perfectly straight line, but the question is it close enough to a line that we can say, yeah, it's fine. Okay? Well, they tell us the R value is 0.964. Now, remember, back in Chapter 4, we used this table. and we looked at our sample size, that was n, and our critical value, and we compared it to that r value. Okay? Well, with a sample size of 10, our critical value is 0.632. And then we would compare the critical value to the absolute value of our r value. And our r is positive, so it would be positive either way. So how does 0.632 compare to the r value of 0.964? Oh, well, 0.632 is smaller. And remember we said that if the r, or the absolute value of r rather, is closer to 1 than the critical value, then that means it is linear. Well, yeah, 0.632 is definitely smaller than the r value of 0.964. So yeah, this is linear. It's not a perfect straight line, but it's real close. Okay, I did not draw a great line there. I probably should have put it a little bit further up. But there should be about as many dots above as below, okay, if I had done a good job there. Also, looking at this box plot here, we're inclined to say, ooh, long whiskers usually mean outliers. But if you really look at it, this whisker's long, but this part of the box is also long. So they sort of offset. So I don't know that it's really fair to say it's skewed right. I think it's close enough. It may be skewed a little, but this big box here, you know, if I look right here in the middle, it's about half below and about half above. So I don't know that it's really, you know, skewed enough that we could say it's not a normal distribution. So this is normal. It's close enough to normal based on this QQ plot here having an R value very close to 1. So we're good. Okay. So it is appropriate for us to, let me see, are the conditions for testing the hypothesis satisfied? And we're going to say, yeah, it's appropriate for us to use a hypothesis test. Okay. Alpha, they say, was the class effective? So in other words, are you going to reject that the mean is 198? You're going to reject it and go, no, mean's higher than 198. He definitely increased his reading speed. The class was effective. Or are you going to say, you know what, I don't have enough evidence to reject it. It may not be 198 reading speed anymore, but I don't have enough evidence to reject that, so I can't support the claim that it was an effective class. It was maybe not worth the money. Okay? All right, so alpha equals 0.1. Remember that because this is a right tail test, we had a greater than symbol for our alternative hypothesis. This is a right tail test. And when we have a right tail test, that means our critical value is going to be a positive number. Okay? Our T distribution here assumes we're doing a right tail test. That's why it's only got positive numbers in the table here. Our alpha was 0.1. Because it's not two-tailed, it's not split between two, so I get to look at the 0.1 column. And my degrees of freedom is always 1 less than the sample size. Well, our sample size was 10. So 10 minus 1 is 9. So we're going to look at 9 degrees of freedom and the 0.1 column. All right, so track down to 9 degrees of freedom. The 0.1 column, they meet at 1.383. So 1.383 is our critical number. Okay, that is our critical number. Now we need a test statistic so we can see if that test statistic is in the rejection region or not, and that will help us make our decision. So we go to our calculator. As a reminder, when you're doing hypothesis test on means, to get your test statistic and p-value, you pick t-test. So stat, test, option 2 for t-test. Now it asks us, hey, do you have data or do you just know the statistics? Well, we have data. In fact, we do not know the statistics. We do not know the mean or the standard deviation of this set of numbers. We just have the raw data. So actually, I need to exit this menu. I'm going to pick Stat. I'm going to pick Edit. And I need to pick a list of numbers to put in these 10 values. So I'm going to arrow up to the very top where it says L1. I'm going to hit Clear. I'm going to hit down arrow, and it's going to wipe out the old data that I had in L1. I'm going to fill in the data they gave me. So 206, 217, 197, 199, 210, 210, 197, 212, 227, and 209. That's my data. So now when I go to stat, test, and t-test, this time I'm going to say, oh, I have data. I'm not going to pick stats. I'm going to say I've got data. And it's going to say, okay, now tell us the rest of the information that we need so that we can give you your test statistic and your p-value. All right, so I said I have data. The mean number that I used was 198. Oops. The mean number I used was 198. The list, in other words, where did you put your data? My data is in L1, so I'm going to leave it alone. It assumes it's in L1. If I had put it somewhere else like L3, I would hit second and then 3, and that would change that to an L3. But mine's in L1, so I'm going to push second 1 to tell it, hey, my list of data is in L1. My frequency is 1. In other words, every one of these numbers I put in should count one time. Okay, so frequency 1. And then what symbol did I put in my alternative hypothesis? I put a greater than symbol. So I'm going to pick the greater than symbol in my calculator as well. And then I'm going to tell it to calculate. Now notice up at the top, my calculator says, hey, your mean is greater than 198. Yes, that was what I wrote for my alternative hypothesis, so it's good that it says that. It tells me that my test statistic is 3.50. While I'm looking at it, it also, oh, by the way, notice that test statistic, it says t equals. When we did proportions, it would say test statistic z equals. So that fact that it says a t right there is my other clue that I should be using the t distribution column on my part of my formula chart. Okay, p-value 0.003. And then I want to point out, remember how we had our set of data, but they did not tell us the mean or standard deviation. My calculator now tells me. It says, hey, by the way, the mean, the x bar for your data set was 208.4. That's really nice that the calculator does it. And it also tells you, oh yeah, by the way, your standard deviation was 9.38, and your sample size was 10, which we knew. So it's kind of nice if they ask me somewhere in my question, hey, what was the mean of your sample? I don't have to do that by hand. I can just run my hypothesis test in my calculator, and it'll tell me what that value was. Okay. All right, so now is decision time. My critical value was positive 1.38. My test statistic was 3.5. Remember, a test statistic of 0 would be in the middle, negatives would be on the left, positives are on the right. 3.5 is beyond 1.3. 3.5 would be about right here. That is in the rejection region. So we are going to reject the null hypothesis because test statistic is in the rejection region. So we are going to reject. Our test statistic was in the rejection region. We are going to reject. Another way to think about it is to compare your p-value to alpha. Our p-value was 0.003. Our alpha was 0.1. That p-value is lower than alpha. It is less than alpha. It is smaller. That means that the probability, if the mean really is 198 words, that this class should make you read, 198 words, then the probability of him having greater than 198 for a sample mean is only 0.003. That is an incredibly small probability. So because that probability is so small, we do not believe that the mean really is 198. We think it's greater than that. We are rejecting it. The probability of you getting more than 198 when that really was the mean is very small. You're probably not that lucky, unlucky, however you want to say it. So chances are this was a big fat lie and the mean was not 198. Okay? So we are rejecting that null hypothesis. Conclusion. Since we did not circle the word not, we will not write the word not. Not is left out. It's going to be left out of our sentence too. So there is sufficient evidence to support the claim that what? Well, what was our claim? Our claim was that the mean would be greater than 198. words per minute. Because that we are, supporting the claim here, that means that class was effective. He did improve his reading time. Okay. So, are we supporting the claim? Yes. Have we found statistically significant results? Yes. Now, one thing I would look at, his average words per minute were 208. 208 is, about 10 above the mean of 198. That's, we could debate whether that's enough improvement to be of practical significance. Maybe depends on how much reading he does and that sort of thing. So we could debate that. But it does seem more significant than the, 18 seconds or whatever it was in the traffic light example previously. Okay, one more example. Consumer Reports. Consumer Reports used to be a magazine. I'm not sure if they're still open or not, but it used to be a magazine that would test different products. Like, hey, what's the best washing machine to buy, or what's the best car to buy, or different things. And they would test different products and give you the results in a magazine so that you could kind of compare and figure out what product was best for you. And the nice thing about it was I don't think companies could pay for their product to be in it. So you knew it was impartial. It wasn't just an advertiser paying to have their product promoted. They really, did a good job of being neutral in all their tests. But Consumer Reports indicated that the mean acceleration time from 0 to 60 miles per hour for the Dodge Intrepid was 10.2 seconds. Okay, so from the moment you hit the gas, if you're going 0 miles an hour, you hit the gas, the average time that it took you to get up to 60 miles per hour was 10.2 seconds. In most tests of this type, regular unleaded gasoline is used. So you walk up to the pump, you just put regular old gas in it, and you got this average of 10.2 seconds. Suppose that 41 such tests were made using premium unleaded gasoline. That's the higher quality gas, the more expensive gas. Okay. So the question is, I wonder if I put fancier gas in my car, is that going to make it perform better? Is that going to make it go from 0 to 60 in maybe less time than 10.2 seconds? Okay. So the sample mean acceleration time was 9.7 seconds with standard deviation of 2.1. Does this indicate that premium gasoline tends to reduce average acceleration times? So notice the mean used to be 10.2. We put premium gasoline in it, and it went to 9.7. So that would indicate that it does reduce the amount of time that it takes for your car to accelerate. The question is are we unlucky or lucky, depending on how you look at it? Did we just happen to get a group of cars that were just, better cars, and so the time went down? Or was it really due to the gas and using the different kind of gasoline? Okay. All right, so our null hypothesis is that our mean equals 10.2. It stays at that 10.2 seconds. That's our original hypothesis that we're testing. Our claim, what we're trying to see if we can support or not, is that using this other gasoline reduces the time. So it makes the mean go less than 10.2. It reduces it. Because we pick a less than symbol here, this is a left-tailed test. Our critical value is going to have a negative on it because when we do our picture in a minute, we're going to have a tail on the left. Okay. Now, what is our significance level? 0.05. And I need to look up that critical value on my table. I'm using mean Mr. T. Because it's just a left-tailed or right-tailed, I don't have to divide by 2 and all that. Okay, my tail is not split between two parts, it's just one tail. So I'm going to look in the 0.05 column. And my degrees of freedom. Well, I had 41 in my sample. So degrees of freedom is always n minus 1. 41 minus 1 is 40. So I'm going to look on the 40 degrees of freedom row and the 0.05 column. So 0.05 column down to 40 degrees of freedom. 1.684 is my cutoff number, my critical value, 1.684. And it is negative because this is a left-tailed test. My 0 t-score would be in the middle, positives on the right, negatives on the left. So negative 1.684 is my critical value cutoff number. My test statistic and p-value will come from the calculator. So let's see what the calculator is going to need. It's going to need to know that I had 41 samples, okay, 41 cards in my sample, so n is 41. Notice that's above 30, so we're good. We don't have to do that analysis on the QQ plot and box plot and all that like we did on the previous example where there are only 10 numbers. Because if we're above 30, SDSM, central limit theorem, we know that we're good. Okay. They told us the mean acceleration time, so x bar is 9.7, and the standard deviation is 2.1. I know I'm going to need that in my calculator. Remember in your calculator, if you're doing to get your test statistic and p-value for means, you pick t-test. And they reminded you that your null hypothesis had to have mu equals, which we did. All right, so stat. I'm going to arrow over to test. I'm going to pick t-test. Do I have data or the stats? I do not have the raw data. I do not have the acceleration time for these 41 cars. I do have the stats. The mean. Well, the number I put in for mean in my null hypothesis was 10.2. My x bar, my average acceleration time, was 9.7 in my sample. Okay, so I'm testing whether 10.2 is the population mean, the mean of all cars. But I'm basing it on my sample where the mean was 9.7. And my standard deviation is 2.1. I had 41 vehicles in my sample, so n is 41. My alternative hypothesis had a less than symbol, so I'm going to pick the less than symbol in my calculator, and I'm going to hit calculate. It reminds me that I picked an alternative hypothesis of mu is less than 10.2. That does match my alternative on my paper. My test statistic, they tell us, is negative 1.52. My p-value is 0.07 if I rounded to 2 decimal places, 0.068 if I did to 3 decimal places. And now I'm ready to make a decision. Remember, negative 1.64 was our cutoff, our critical value. Negative 1.2 is just barely before. It's not quite far enough out. So it is not in the rejection region. Since my test statistic is not in the rejection region, I will not reject the null hypothesis. If you want to use the p-value approach to make your decision, you're going to compare the p to alpha. P was 0.07, alpha was 0.05, remember? How does p compare to alpha? P is greater. Okay, p is low, reject the null, reject the ho. P is not lower, so we will not reject. Notice that both the test statistic and p-value approach, both of those lead to the conclusion of do not reject. If your p-value approach told you to do one thing and your test statistic told you to do the other, that would be a problem. One of them would obviously be wrong. So it's important that those two methods come to the same conclusion. Sentence always starts the same. There either is sufficient evidence to support the claim or there is not sufficient evidence to support the claim. Since I circled the word not, I'm going to write the word not. There is not sufficient evidence to support the claim that what? And now we got to go back up to what was our claim so we can fill that in. Our claim was that the mean acceleration time would be less than 10.2 seconds. So there is not sufficient evidence to support the claim that the mean acceleration time is less than 10.2 seconds. Okay. Are we supporting the claim? No. We circled no, we're writing no. Have we found statistically significant results? No. Significant results only happen when you reject. Okay. Now think about what happened here. We had, based on old data, we believed that it took 10.2 seconds for a particular kind of car to accelerate up to 60 miles per hour. we took a sample of 41 other cars. Now, we made a change to those samples. We put fancier gas in them. We put premium gas in them. And we said, you know what? When we use these same cars, the same Dodge Intrepids, and we put premium gas, our sample of 41, it only took it 9.7 seconds to accelerate. It used to be 10.2. Now it has only taken an average of 9.7. I wonder if that means this premium gas is better, and it lowers the speed time, the acceleration time. It gets better performance out of your car. Well, the probability, if the mean really is 10.2, mean is legitimately 10.2, if that's the case, then the probability of you getting a sample that took less than 10.2 seconds, the probability of you getting a sample that took 9.7 was about 7%. Okay? Now, is that low enough? Well, it's low. It's not lower than 5%, but it is low. And how do I know how low it needs to go? I compare it to my alpha level. I compare it to the probability of a type 1 error. And that probability was higher than the probability of a type 1 error, so I did not reject. Now notice if I had decided to use alpha equals 0.1, if I had decided that the significance level was 0.1, then my p-value would have been lower, and I would have rejected. So sometimes, it does matter what level of significance you chose. You might come to different conclusions based on whether your alpha is 0.05 or 0.1 or 0.01 or whatever. Okay, so that is a factor that they have to use. In many science-type experiments, they use 0.05 for their level of significance, but you could use something else. If it's a medical treatment and or maybe a matter of life and death, you might want to use a lower alpha. You might say, you know what, we want to be 0.01. So there are times that you might want to go lower than 0.05, but a lot of science experiments use 0.05 as kind of the standard.